Today our topic is valence shell electron pair repulsion theory. It is a theory to explain the bonding. The important point in valence shell electron pair repulsion theory, when we consider the formation of a molecule, if it has more than two atoms, there will be a central atom. And in the central atom, there are 8 electrons or 4 pairs of electrons. All these electrons are negatively charged. The valence shell of central atom, there are 4 pairs of electrons in most of the cases. There are exceptions that we already discussed. In most of the cases in the central atom, there will be 4 pairs of electrons. In some cases, that will be 3 pairs. In some cases, that will be 2 pairs of electrons. Some cases, 5 pairs may be there. 6 pairs may be there. There are several possibilities. However, in the central atom, the valence shell of central atom, there are electron pairs. And these electron pairs are negatively charged. These negatively charged electron pairs will repel each other. So the molecule has a sort of instability in it. So in order to gain maximum stability, the electron pairs will exist as far as possible, exist as far apart as possible. It is the main concept in valence shell electron pair repulsion theory or VSEPR theory. We can see the postulate. What is the first postulate? The shape of a molecule depends upon number of valence shell electron pairs around the central atom. In the valence shell of central atom, there will be electron pairs. That electron pair decides the geometry or shape of the molecule. There are 2 types of electron pairs already we mentioned: lone pair, unbound pair. Lone pair is not involved in chemical bonding. Bond pair is involved in chemical bonding. There are 2 types of electron pairs: lone pair and bond pairs. Pairs of electron in the valence shell repel one another since their electron clouds are negatively charged. So these electron pairs will repel each other. We know it. They are negatively charged, so they will repel each other. What is the third postulate? These pairs of electrons tend to occupy such positions in space that minimize repulsion and thus maximize distance between them. When these electron pairs are arranged in space, that means around the central atom, in the valence shell of the central atom, the arrangement will be in such a way to get minimum repulsion between the electron pairs or to get a maximum distance between the electron pairs. So here, these are the 3 important postulates of the theory, main postulates of the theory. And it has 3 more postulates that is about the formation or how can we depict or represent the arrangement of electrons. So to depict or represent the arrangement of electrons around the central atom, the valence shell is taken as a sphere, spherical. Valence shell is taken as a sphere with the electron pairs localizing on the spherical surface. With the electron pairs localizing on the spherical surface, on the surface of the sphere, at maximum distance from one another. So if it is arranged on the surface of a sphere at a maximum distance, how will you measure this distance? Only through measuring the angle, bond angle. It is possible to measure by measure the distance by measuring the bond angle, because the electron pairs are on the surface of a sphere. So if you want to measure the distance, the straight line, you have to draw a straight line and measure. But if you measure the angle, that will be more easy. What is the angle? Bond angle. That bond angle, if the bond angle is more, the distance also will be more. So here, by measuring the bond angle, we can measure the distance between two bond pairs. Then about the multiple bonds, in some cases, double bond and triple bonds are present. In such cases, how will you consider them? Whether it is as two pairs of electron or one pair. Here, multiple bonds are considered as a single pair of electron, single electron pair. But we will call it as a super pair. What is the reason? There are more than one electron pair, therefore it is considered as a super pair. And in case of resonance structures, if it is not possible to represent the molecule with a single structure, we'll use several structures. That is resonance structure. These several structures, we are using several structures. Each structure that is according to VSEPR theory, or we can apply VSEPR theory to any of these structure, resonating structure, all structures. It is possible to apply VSEPR theory to all the structures. Where two or more resonance structures can represent a molecule, the VSEPR model is applicable to any such structure. So these are the 6 postulates, and the first 3 are very important, and the first 3 need a little more explanation if you want to explain the geometries of the molecules with the VSEPR theory. So we can go to the second postulate. What is it? There is repulsion between the electron pairs. So what is the repulsion, or what is the order of repulsion between electron pairs? We know there are 2 types of electron pairs, lone pairs and bond pairs. The repulsive interaction of electron pairs decreases in the order. Lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. So if we examine the electron pair repulsions, we can see the maximum is in between 2 lone pairs, and the minimum is in between 2 bond pairs. And the repulsion is decreasing in the order. Lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. So here, LP is the short form of lone pair, and BP is the short form of bond pair. So you don't mistake it. It is lone pair LP, lone pair BP, bond pair. There are many other full form for BP, LP, etc. But here you have to consider it as lone pair and bond pair. So when we consider the repulsions, which is more, lone pair repulsion is more, and that is greater than lone pair bond pair repulsion, which is greater than bond pair. Now we can go to the third statement, third postulate. What is it? When the electron pairs are arranged, they are arranged in such a way to get a minimum repulsion and to get maximum distance. Minimum repulsion, maximum distance. How it is possible? That we can see from here. If it has only 2 electron pairs, the central atom has only 2 electron pairs, the structure will be linear. An example, BeCl2. If the electron pair, number of electron pairs are 3, the structure will be trigonal planar with bond angle 120 degree. Maximum distance, it is the maximum distance, 120 degree. If the number of electron pairs are 3, then the structure is trigonal planar. An example, BF3, BCl3, all these are examples. If the number of electron pairs are 2, the possible structure is linear with the bond angle 180 degree, and that is the maximum distance. So in this structure, we can expect minimum repulsion. And if the number of electron pairs are 4, the structure is tetrahedral structure with the bond angle 109 degree 28 minute. Example, CH4, NH4 plus. And if the number of electron pairs are 5, the expected structure is trigonal bipyramidal structure with the bond angle 90 degree and 120 degree. If the number of electron pairs are 6, the expected geometry is octahedral structure with bond angle 90 degree. 90 degree. An example is SF6. Now we can see the structure of certain molecules according to VSEPR theory. First one, structure of methane. When you explain the structure of methane using VSEPR theory, first you draw the Lewis structure of CH4. Lewis structure of CH4. And here you can count the number of bond pairs. 1, 2, 3, 4. 4 bond pairs are present in it. So number of electron pairs, 4 bond pairs. Therefore, what is the geometry? If the number of electron pairs are 4, what is the geometry? Okay, you can see here, it is tetrahedral structure. This tetrahedral structure. So geometry, tetrahedral structure with the bond angle 109 degree 28 minute. That is to minimize the repulsion between electron pairs. Then you draw the structure and indicate the bond angle 109 degree 28 minute. It is tetrahedral structure. Now see the structure of BCl3. Draw the Lewis structure. Here 3 electron pairs are there in chlorine, that is not shown here. Only the bonds are shown. So here it is very clear there are 3 bonds between boron and chlorine, therefore 3 bond pairs are present. Number of electron pairs, 3 bond pairs. So what is the geometry? Triangular or trigonal planar. Triangular or trigonal planar with the bond angle 120 degree. That is to minimize the repulsion between electron pairs. So we can represent BCl3 in this way with the bond angle 120 degree. The bond angle 120 degree. Now see the case of PCl5 and SF6. In PCl5, you know, 1, 2, 3, 4, 5. 5 bond pairs are present. So its geometry is trigonal bipyramidal geometry with the bond angle 120 and 90. Here this bond is above the plane and this bond is below the plane. We'll call it as axial bond because it is moving along the axis. This is the axial bond and these bonds are equatorial bonds. Axial bonds and equatorial bonds. 3 equatorial bonds and 2 axial bonds. So in the case of PCl5, the structure is trigonal bipyramidal. PCl5 has 5 bond pairs, so its structure is trigonal bipyramidal with bond angle 90 degree and 120 degree. The next example is SF6. In SF6, 1, 2, 3, 4, 5, 6. 6 pairs of electrons are present. Number of electron pairs, 6 bond pairs. Therefore, what is the geometry? Octahedral structure with bond angle 90 degree. That is to minimize the repulsion between electron pairs. So we can represent the octahedral structure in this way. This is square, and in this square, here at the center there is sulfur. 4 fluorine atoms are in the plane of the square. 1 fluorine is above the plane and 1 fluorine is below the plane. So 6 SF bonds can form. And here bond angle is 90 degree. Bond angle is 90 degree. Now you can see the representation of various molecules, the VSEPR model of various molecules. It is the structure of linear molecule. BeF2, BeCl2 or example with the bond angle 180 degree. Bend structure, SO2. SO2 has a bend structure. Trigonal planar structure, SO2. SO3. SO3 has a trigonal planar structure. Trigonal pyramidal structure, NF3. NF3 has trigonal pyramidal structure, T-shaped structure. ClF3 has T-shaped structure. XCF4 has square planar structure. Square planar structure. PF5, like PCl5, it has pyramidal, trigonal bipyramidal structure. SF6, it has octahedral structure. This is the molecular models. If you see these figures, you will get a little more idea about the shape of the molecules. Now, these are 2 examples in which lone pairs are present. Along with the bond pairs, lone pairs are also present. Here you can see AB3E. B3 means 3 bond pairs and E means 1 lone pair. So 3 bond pair, 1 lone pair. 3 bond pair and 1 lone pair. So actually, we are expecting tetrahedral structure in the case of 4 bond pairs. But here 1 is a lone pair. Usually, lone pair bond pair repulsion is greater than bond pair repulsion. Because of the high repulsion from lone pair, the bond pairs will come a little close to each other. As a result, the bond angle decreases from 109 degree 28 minutes to 107 degree as it is shown here. So it is explained clearly here. Had there been a bond pair in place of lone pair, the shape would have been tetrahedral. But 1 lone pair is present. And therefore, the repulsion between lone pair bond pair is greater than bond pair repulsion, and as a result bond angle decreases from 109 degree 28 minutes to 107 degree. So if there is a bond pair, you will get a distorted structure. Instead of tetrahedral structure, here what you are getting, a trigonal pyramidal structure or simply pyramidal structure is obtained. Here in this position, only a lone pair. There is no atom to complete the tetrahedra. So since this position is vacant, you will get a pyramidal structure. Another example is H2O. Here, 2 bond pair and 2 lone pair are present. 2 bond pair and 2 lone pair. 2 bond pair, 2 lone pair. Here you can see these 2 are lone pairs and these 2 are bond pairs. Here lone pair repulsion is greater than lone pair bond pair repulsion, which is again greater than bond pair repulsion. Here 2 lone pairs are present. These 2 lone pairs will repel each other strongly. As a result, what happens? The bond pairs will come close to each other. They will be closer. As a result, bond angle reduces from 109 degree 28 minutes to 104 degree 30 minutes. 104 degree 30 minutes. So in this way, we can explain the geometry of several molecules using VSEPR theory. Now I think you may have an idea how to explain the geometry of molecules using VSEPR theory. When you explain, you concentrate on three things: draw the Lewis structure, find out the electron pairs, number of electron pairs. After determining the number of electron pairs, select a geometry and mention its bond angle. That means what is the distance between the electron pairs. If there is a lone pair, there will be some distortion in the geometry and you have to explain it very well. Here the geometry of NH3 is pyramidal, but that of H2 is bend, BNT, bend or V-shape or angular shape. Okay, I think it is enough for today. The assignment, you write the assignment and submit it in time.